Hello, my name is Katshi. I will be showing a demo of Hex5 Multizone security on Renesas microcontroller. Hex5 is part of Renesas RA partner ecosystem. Securing a microcontroller is challenging. The connectivity interfaces make it prone to remote attacks. Large amount of software further increases the attack surface. These days, a chunk of firmware and software come from the supply chain. Any untrusted components pose interference risks to critical functions. On the other hand, implementing security is hard, especially for resource-constrained MCUs. The requirements of time to market and compliance make it even more difficult. Multizone is designed to address these challenges. Multizone is a software-defined trusted execution environment, TEE. It enables hardware-grade security by separation. Multizone can secure the entire embedded system, including programs, data, I/O, IRQs. It protects trusted functions from untrusted ones. Customers can retrofit existing hardware to upgrade security posture. No need to redesign. It's policy-driven, no coding required. Multizone is a safe and elegant alternative to ARM TrustZone for Cortex M0 Plus, M3, M4, M7. This is today's demo scenario. Multizone is running on Renesas EK-RA6M3 evaluation board. There are 3 secure domains or zones configured. Zone 1 runs a bare metal terminal console program that connects to the PC via the UART port. This shows the zone hardware peripherals mapping. Zone 2 interfaces with a local button. This shows the secure user level interrupt handling. Zone 3 controls the robot via GPIO. Imagine this is a deterministic, real-time, safety-critical application. How do we put this together? It's a 3-step process. Step 1. Break the monolithic firmware up into logical blocks. Separate out the critical functions. Step 2. Write the config file to define the RWX read-write executable memory region for each zone. For example, we see that in the description of Zone 1, IRQ number 24, which is the keyboard, is mapped to this zone. Memory regions are specified for ROM, RAM, peripherals, and so on. We'll show that in demo. We'll show that in action during the demo. Step 3. Use Multizone toolchain extension to take the config file, binaries for each zone, to generate a signed Multizone image. Flash that onto the hardware. Let's start the demo. I'll switch to the camera and console. Multizone is running on this Renesas board. It's a 120 MHz RA 32-bit MCU that uses ARM Cortex M4. It has 2 MB of flash, 640K of SRAM. It's connected to my PC using UART and the Robotic arm through GPIO. Traditionally, the binary file on the embedded system is one big executable. When there's no boundary to shield safety-critical operations, exploits such as buffer overflow, malware, DOS, etc. can destroy the entire system. Multizone creates security by separation to protect important processes. I'll show that concept with Zone 1. We are on Zone 1 terminal console as indicated by Z1. All zone code runs securely in unprivileged mode, including hardware interrupt handlers. You can see this from the splash screen that shows the content of privileged registers, otherwise not available in unprivileged mode. Read-only access to these registers is transparently provided by Multizone runtime using Trap-and emulation. Using Trap-and emulation means no redesign in software required. Hit return and we can see the user commands written for this zone. The MPU command shows the RWX read-write executable zones policies for Zone 1. This zone or partition is defined by the policy file that we looked at earlier on the PowerPoint. Each line shows the start and end address of a memory region with its access policy. This enforces hardware-level separation of CPU and memory-mapped resources, policy-based access to I/O, peripherals, and user mode execution of interrupt handlers. I'll show that I can read from an address assigned to the zone. So I will pick the first address, load its read in the on a RISC machine. Okay, so we see there's a value of 0 stored in that address. Fine. Now I want to illustrate a scenario. Say this is a medical device, IoT, an intruder breaks into the system, breaks into Zone 1, and he and she intends to steal secrets, for example, patient data. However, because that information, the memory location for that information is assigned to another zone, the system will deter the exploit. So I'm just going to try to read from a memory address that's not in Zone 1. So we can see that a read fault is raised. Next, I will simulate a buffer overflow exploit. I will demonstrate that even if an intruder breaks into Zone 1, he cannot modify or corrupt a location in a text region. Well, first I will demonstrate I can actually write to a legitimate address. So for example, I will write to this address. I'll write to this address. Okay. So let's read it back out. Okay, so that was successful, but what would happen if I try to write to the text region, which is this read-only region? I'll just pick any location. As expected, a write fault is raised. Now let's try to exec some code. This address is the reset vector address, so execing to it is the same as typing the restart command. Okay, so that was an execution of the restart command. Now, if an intruder comes in and try to jump to a location that he should not access, for example, I'll just try in a location that's not in this zone. So that exploit is deterred again. All right, I've shown you security through separation. Let's move on to zone 2. Zone 2 demonstrates interrupt management. It blinks the LED through GPIO. Pressing the button that's mapped to this zone will send message to the screen. We'll come back to this zone when I do the robot demo. Now let's take a look at performance and statistics. The yield command measures the current round-robin trip time for the whole 3 zones. The stats command measure and summarize 10 rounds of yield, min, medium, max. Observe that multi-zone context switch and interrupt latency metrics at the very bottom, under the kernel section. It only takes 387 cycles of cycling through 3 zones and 10 rounds. Note that the multi-zone context switch is too fast to be measured in microseconds, therefore the time is showing up as 0. Multi-zone is handcrafted in assembly, therefore it's so fast. Multi-zone runtime is 2 kilobytes of assembly code that can be placed in the boot ROM or flash. More importantly, its attack surface is tiny and is designed to be formally verifiable. Certainly the zones need to interact with each other. That's done only by secure messaging routed through multizone. I will send a message from zone 1 to zone 2. Send to a ping. And I get a local message with a reply of Pong. I can also send my own zone. I'm in zone 1. I'll send zone 1 another message. I will receive it using the RECV command. And I got the message hi back. The idea is the message format will be architected by the system designer. Secure byte streams are sent and received by zones. There's no sharing of anything, no shared memory, buffers, pointers, or anything exposed to attack, and it's impossible to spoof. Lastly, I will fire up the robot by using secure messaging to communicate to zone 3, which is where the robot is connected to the board through GPIO. So sending 3 this message unfold will unfold the robot. Now I will send it a start command which will launch the robot into a sequence dance. Now while the robot is operating, you will see that I can restart zone 1, press the buttons on zone 2, and you see the robot will not miss a beat. The LED lights will also continue to blink. I'll restart zone 1. Okay, I'm gonna stop the robot. It's a little bit loud. So once it comes into position, it will stop. So I've shown you security by separation, performance of multi-zone, secure messaging, and the resiliency of a real-time application, all powered by Hex 5 multi-zone security on Renesas. You can learn more on the Hex 5 website. The FAQ site is very helpful, or download the demo package from GitHub. And please connect with us online. Thank you for watching this demo.